Alright, this is the first lesson of Unit 4, Area Study 1, how can waves explain the nature of light? Okay, so basically we're looking at what waves that we know about and we can observe, and then comparing that to the behaviour of light and how waves can explain. Alright, so first of all, mechanical waves. Yeah, can't spell. There we go. I hope that's right. So mechanical waves is the first thing, and so mechanical waves are things like waves in springs, water, things like that. All right, so they are things that we can, observe. We can observe those waves. We can create them. We can make them, and we can observe them. Now, the thing also about waves, and this is a key thing, and it's bold in your notes here, is that you have a transfer of energy all right, without, and this is the part of the key thing, transfer of particles. All right, so you got transfer of energy without the transfer of particles. So like a tennis ball, for example, you belt the tennis ball and you can see that the tennis ball actually moves the particle, and it's moving, so it's got some kinetic energy, whereas that energy is moving from one place to the other, and then the player down the other end with that tennis ball may or may not get it back, but they will certainly have to hit it. So there's transfer of energy from one player to the other via the tennis ball, but in mechanical waves, the energy moves without the particles. Now, it doesn't mean the particles are not moving, but the particle doesn't move from one place to another like the tennis ball did. All right, so the other thing that we got to do is define for you what a medium is. So all a medium is the substance that the wave moves in. In through. All right, so mechanical waves are what we're interested in. So there are other waves, electromagnetic waves, for example, sound waves. There are other waves, but the ones we're interested in are mechanical waves. Now there's two types, and there's a video on that, so you should watch the video. And the first type that we need to look at, this A in there, is transverse. Alright, so this diagram kind of shows you about the transverse wave. Alright, so here's a diagram of a transverse wave. So what we've got is this midline here, and this midline is the zero disturbance, or the mean position. So if there was no waves being produced, that spring, for example, would just sit in that, along that orange line that I've just drawn. So what we've got then is we've got a disturbance, and if you were to say look at this peak point up here, for example, and you watch the peak, not the particle, but if you watch the peak, you would see the peak moving along that peak. So it would be looks like that's moving along. So that's the energy transferring. However, if you look at that particle that's there, and when the arrow's shown on the next one, so you're looking at that particle or that piece of spring that's there, that piece of spring doesn't move to some other place on the spring. That piece of spring moves backwards and forwards like this, and so that's what this one here is. That's what this one here is showing. All right, so this particle is moving backwards and forwards, up and down here, backwards and forwards. So this piece of spring just goes backwards and forwards, up and down there. So you'll notice that the direction that that piece of spring is moving and the direction of travel of the energy are at 90 degrees to each other. All right, and so that's the key thing with transverse waves, is that the direction of travel and the direction of movement of the individual particles is at 90 degrees to each other. All right, so as I said before, previously, the particles actually do move, but they don't change their location. So, as I said at the start, this would be the mean line, so this bit of spring there would like to actually just be sitting there, and when the wave comes through, it moves, but it moves about that mean position. All right, so backwards and forwards like so. All right, so there's our transverse wave. The other kind of wave is what's known as a longitudinal wave. So longitudinal. And this diagram, yes, shows a bit of an idea of a longitudinal wave. Now you look at this area of the spring there, and you'll notice that the coils in the spring are close together. So that's what we would call compression. And then this area of the spring there further apart, and so that's what we call a rarefaction. All right, we'll get more on that a little bit later. All right, so and our individual particles sitting on the spring, wherever it may be, and here's, so this bit of spring here, it doesn't get up and move to some other place. So what it does is, as an arrow below, it vibrates backwards and forwards like this, about a mean position. Now, if you were to look at these compressions, you would see that these compressions would move along the spring. So again, that moves along the spring. The energy is moving along. Now you'll notice also that the velocity is also in the direction along the spring. So you'll notice that this time the direction of movement of the particle, oscillation of the particle, backwards and forwards, and the direction of the velocity of propagation are parallel to each other. All right, so that's what happens with a longitudinal. All right, transverse, the oscillating particles and the movement of the energy at 90 degrees. Longitudinal, the oscillation of the particle and the movement of the energy are parallel to each other. All right, so this is like, you can think of these as pressure waves, and sound is something that travels like this. All right, so the next thing is, again, another definition, and this diagram shows this, so a wave pulse and then continuous wave. So the top A up here shows you a wave pulse, so as this hand diagram shows you, one flick, and so one flick you just get one wave pulse. Whereas the one below In B, it's a continuous wave because we're moving backwards and forwards with the hand up and down, and so then we get all these continuous waves. All right, so there's just another definition. All right, so that's it about for this first lesson, because it's just a couple of definitions. So really it's longitudinal transverse, so this last diagram. All right, shows a bit of a summary. So longitudinal waves, and a little definition and diagram, some examples of what we can do. Transverse waves, a little diagram, and then some examples. All right, so there's some text questions on these. Don't forget to watch the video, and of course, if there's anything you need further clarification, make sure you ask.